can use our model, and they can use this license plate recognition model and recognize the plates in real time. So, and the part two would be the car color detection and car model recognition. Right now, we have done these three parts, which is data collection and pre-processing. The data collection is just the collection of data that is we have obtained from Kaggle, while the pre-processing, in pre-processing stage, we have converted the annotations and the data, the images as well as the annotations into a required format so that our model could read it. Because when we convert our images into a standard square, for example, a 200 pixels by 200 pixels image, the annotations, they also need to be converted according to that reference. So that was the pre-processing done. Then after that, we have also completed the license plate detection and localization, which means that we can now draw a bounding box and find the region of interest that we can perform the latest steps on. And now we are currently working on the performance enhancement because we have some errors and some issues. For example, just one of the examples would be that if there are multiple cars with multiple license plates, our model does not perform well on that. And also sometimes if there is not much contrast or not the plates are not perfectly aligned with the screen, they are at some weird angle, then our model is not performing at this moment. And also we are working on the text recognition part. So for this, we have used two approaches. One is building a model from scratch. We build the model from scratch, but we use pre-trained weights from VGG16 model. It is these weights are trained by VGG16 model on ImageNet dataset. We use them to improve the performance of our model. It is just a basic sequential model, and we have used some dense layers to perform the training, and then we get a test accuracy of 88.6%. So you can see in this images, for example, in this there is a white car, and our model sort of confuses it with the license plate with the background. And also you can see that in this picture, uh, like in where there are more than one cars, the model doesn't perform well. We are trying to work on this part. So after that,
So Muhammad,
we
use
yeah
VGG16 for localizing the for localization of license plates.
yes.
Mhm.
I,
So
I, will- I
you train it to draw this to get this bounding box around license plates.
yes. So these are the initial weights that I'm inserting into the model.
So to do this, do you need to do those this I mean minimum bounding box around? Do you need to do it by yourself? I mean, what will be the I mean what is the output in this case? It's XY coordinates, for example, of this
Yeah, it is
bounding.
yeah the output of this would be these corners, the
Okay,
extreme top left corner, the coordinates, and extreme right corner,
okay.
right bottom corner. So these diagonals, then the bounding box is formed around that.
So do you
So
need to
yeah,
do you need to annotate it for some images because I mean you are using a pre-trained model for transfer learning. So do you need to do it for part of the data set by yourself? So because it's supervised. So do you need to make it first, annotate it,
yeah.
and train the model for doing this?
The annotations were given. Actually, the annotations were given, and they were given in the same format. But when we convert these images into, for example, a 2 by 2, sorry, 200 by 200 pixels for our model to be trained,
It will be
so that
different.
all the images, yeah, so all the images are in the same format. So then we have to convert those annotations accordingly. So that's just a transfer of annotations and just a pre-processing. We don't have to draw these annotations by ourselves, but we do some sort of performance to get these XML
So you need to
annotations from XML.
adjust. You need to readjust the x y coordinates of this minimum bounding box.
Yes.
Okay.
Okay, and the next we have used mask RCNN. Leo has worked majorly on this, and he will be able to explain it.
Yeah, so our second approach was to use an existing framework for object detection. And so as McDowson suggested, we used the mask RCNN, which is a tool for object instance segmentation. So it extends a faster RCNN, which uses convolution neural networks to provide bounding box recognition. So this we used an implementation available on GitHub, and so this implementation contains pre-trained weights for the MS COCO dataset, which is a large-scale object detection, segmentation, and captioning dataset. So, for example, one of the label is a car. So it was easier for our model to converge rapidly with these pre-trained weights. So we used a dataset of around 400 images and split into 80% for training and 20% for evaluation. And so we got an accuracy of around 97%, which is better than our model built from scratch. So now what remains to be done? Well, we have started the text segmentation part. So we used OpenCV to apply some image processing methods and to determine the control. But well, the results are not yet satisfactory because the image processing parameters must be different for each image. So for example, some license plates are already blurred on some pictures, and some others are very clear. So applying a blur is necessary for clear images, but not for already blurred images, where the relevant information is deleted. So we still need to work on this part. And for the text recognition, well, we tried several methods, several optical character recognition tools methods, like Tesseract or a pre-trained deep neural network model, but they did not give satisfactory results. So we still need to work on this part. We need to find a dataset and to develop a model on it. So this is what we have done for now.
So Leo, you are using masked RCNN for also localization of license plates.
Yes.
Okay, and I mean the accuracy is much better.
Yes.
And you don't need to to rescale the images and the XY coordinates in this case. You are working with with the raw data.
Yes, in fact, the implementation has some image processing steps, so I don't need to perform some image processing because it is already done by the implementation.
Okay, yeah. So this is very good. So now we finished maybe the first part, the first phase, which is just localization of license plates, and after that, they want to do some text segmentations and text recognition because we need to convert it into text. So your license plates, we need to convert it into a text. But for text segmentation and text recognition, this is the hard part of that. So is there any pre-trained models which can help us to do this?
For the segmentation?
Yes, segmentations and recognition.
Yeah, well, I didn't find a dataset, so I tried to search for a pre-trained model and something like that, but it wasn't satisfactory. The results were very bad, so I think we should try our model, and we should try to train our own model instead of using an already existing.
For the alignment of this minimum bounding box, some cars are not. Some driving license plates are not aligned. So in this case, is it possible to use, for example, encoder to help us to I mean, to get, I mean, most of, I mean, to try to fix it. Is it possible? I'm just thinking, like using encoder for denoising. So is it possible to try to use an encoder to try to fix?
Maybe we didn't try, but well, yes, we can try to do this.
Okay, okay. Yeah. So thank you very much, Leo.
Thank you.
So, any questions from people here or from people online? To Leo and Muhammad? Questions? We've been working with the same problem, so it should I mean, trigger some questions in your mind, especially for people who are working with the same.
Just for a suggestion, I think it is better, for example, to run a code and, for example, show each line of code, and it is better to find something new.
No, but I need to go to the code. Maybe the code is 100 lines or 200 lines. So if you
Section by section, for example, one section is related to importing the libraries, second for training.
okay.
Something.
So Leo, is it possible to show us the data set? I mean, just I mean for training to get this minimum loading box. Can you show us the data set, some images and
Yeah.
Y coordinates, for example? I mean, this
Yeah,
is-
I can show you the model that I built from scratch.
Okay. No, we need to see how the data sets were annotated, for example. I mean, X, Y coordinates for minimum bounding box. And
Okay.
and
I can
each
show you
image.
that.
So just an example.
Okay, I can show you that.
Because by the way, I mean at the end we can merge all efforts into one project. So if each one can contribute to some part, maybe at the end all people can work together at the end to develop a application, for example. We don't need to have many, but we need to have one which is developed. For a demo, for example, we can build one demo which is really exciting and works perfect. So at the end, maybe we can merge all efforts from different groups into one project or one demo. It would be exciting. Okay, so this is the code.
Sorry, I was mute. I didn't know that I was speaking. Okay, so the first part is just the setting up of our files that I have imported all of my data set into my Colab and my drive, and I have attached my drive. So the first line is just to see.
Can you show us how did you use the GPU? Enable the GPU in Colab? It's
yeah. So actually,
Mhm.
no, it's not a local GPU. It's the GPU that was assigned by Colab. So first I used, actually that was a big blunder, that I was training my network, my model, without using the GPU by Colab. I didn't know that we have to actually enable it. So my first training took almost 3 hours. So after that, yeah. So after that I saw the videos on YouTube, and that we have to go into edit, notebook settings, and see if the GPU is enabled or not.
Okay. Oh,
So this is just,
Mhm.
and this is just a test to see which GPU has been allotted. So it is a Tesla T4 70 watt or 9 watt. I don't know what's it, but it works almost 100 times better.
Okay.
So after that, these are just,
please, how to check if it was enabled, if the GPU was enabled? You need to go to.
yeah, just after enabling it, we use this
Okay.
command.
To
It
enable,
tells actually, right,
you need to go to edit and.
notebook settings,
Mhm.
and we can see
The
your
GPU.
Colab
Okay.
if a GPU is attached or not.
CPU, of course, it's not available here. Okay.
So this time I have got Tesla K80, and it's much more powerful than the previous one. So it changes from time to time.
But
Okay,
also,
so
can you try to, because some of us has GPUs in his laptop, for example. So if you can help us, in fact, to how can we enable your local GPU, it will be exciting.
Every computer has a local.
Some people. Yeah. I guess you have a GPU, correct? Yes. So some people they have GPU locally. So it will be. I don't know which one will be faster. K80 or Tesla K80, which provided by Colab or your local GPU. But it would be nice for Tesla.
okay, I can look into that, but this was working very good for me. So I didn't. I also have an NVIDIA Quadro GPU, but the Collab GPU was working fine, so I didn't move to the local
Okay.
GPU. But I can surely look into that. After that, we have to just import some files, libraries, sorry. And then in this step, I'm mounting my drive. I have already done this, so I'm not doing this again. So I have to mount my drives, and it requires some authorization. And after that, this is the data pre-processing part. Here I take my, for example, here, this is the part where I convert my images into 200 by 200 pixels. And after that, using OpenCV. And after that, this is the part where we convert our annotations. For example, that's just readjusting of our annotations. The annotations were given in the format, already given in the format of the top left corner and the bottom right corner. The coordinates were given. So once my images were converted into a 200 by 200 image size, so I had to readjust them as well and get the output in the form of a list or array.
Okay. So just 1 minute,
So,
please. Just 1 minute. So in fact,
yes.
the data set, it's a supervised data set. So we have images
Yes.
as one row, and for each image, the target will be XY coordinates. It will be the coordinates,
Yes.
the minimum bounding box of each pattern.
Yes.
The target feature would be the minimum coordinates of the minimum bounding box of each image. And the minimum bounding box, it's simple because it's like this one. So it's defined by 2 points, this point and this point, right? And when we put it in XY coordinates like this one, this is X and Y. So we can just say that this one it's X max, right? Y minimum, correct? X max, Y minimum, and this one it's X minimum, Y max. So we define each bounding box by those 2 points, right? Because this one it's X minimum, Y minimum. If you want this one, it's X minimum, Y minimum. If you want to block it, this one it's X max, Y minimum. This one it's X max, Y max. Correct. This one it's X. This one it's X minimum, Y maximum. So we have. So in fact, each bounding box will be defined by, as Muhammad mentioned, it will be X max, Y max, X max, Y max, X minimum, Y minimum. So this is the coordinates of each bounding box. And to plot the bounding box, you have those 4 points, so or 2 points, so it should be easy to plot it in the image. Yes, please continue, Muhammad.
Okay, so then I just test my function to see if it's working or not on just first car, and it works fine. So after that, I repeat this on all, I use this on all the XML annotations and convert these annotations and store it into a Y variable, Y array or list. And after that, this is the normalization. I'm normalizing the parameters.
So you are normalizing X values, correct?
Yes. Yes.
As images.
The values of the X, yes. Yes.
But why?
Exactly.
Why also normalize that? So the annotation also, because the annotation it's the coordinates, but it's coordinates, correct? It's not pixel value, right?
Yes.
XY, it's not because you divided here by 255. So 255, it's pixel, it's maximum pixel value. But annotation, it's different because if you reshape the image into 200 times 200, so it will be maximum 200. Muhammad, you understand me?
Yes, I got you.
Yeah. Because the image now you resize the image into 200 times 200, right?
Yeah.
200 times 200. So in this case, each X and Y maximum it will be 200. So if you want to normalize it, you need to divide it by 200, not 255.
Okay. Yeah, I got it. Yeah, you are right. This is a mistake from my end. Okay.
But
so after that,
it's only for plotting. It will not make. I guess I don't know if it will make any change or not. Difference.
Okay. Yeah, but I haven't tried it. I can see if it performs better or not.
Okay.
So after that, I just split my data into, because the data set was quite less. I had only 433 images. So I split it into
But in this case, Muhammad, it's much better to try a cross validation, right? Because the data set is small, so we can just go for cross validation. We will go for cross validation for model check. We will check accuracy, and after that, we will use the whole data for building our model. So we will not lose. So the test size here is 10%, right? But if you want to save those 10%,
Yes.
you can just go for cross validation.
Okay, yeah, I can do that.
Okay,
Right.
so just to try cross validation. This is very nice because this one, it's how can we use transfer learning. So this is how can we use. So we added this one VGG 16. It's a transfer learning. So this one will not be retrained. So Muhammad, can you talk about the model, please?
Yeah, so this is a basic sequential model, but I have used VGC16 weights that have been trained on ImageNet dataset, and from that, then I add 4 dense layers, and this is something that I.
What does it mean? Include top equal false.
Yeah, it means it means that the one layer that is not trainable. It is fine. This is I have done to fine tune my model.
This one false. This one false. It means it's not trained. We will not train it. Layer number minus.
Yes.
So we will not train this one again using. But what about include top equal false? What does this one mean? We can check. Maybe someone can check. Include top integers equal false. So and after that he will flatten the output, and he used 1, 2, 3, 4 layers for and the output layer it's a 4. We have 4 because we need to predict x minimum, x maximum, y minimum, y maximum.
What is the layer number minus 6?
Minus 6. It's a layer number. Number.
You can count from
the other side. Yes, from the end. Okay. So
it's actually the first layer.
Huh?
It's actually the first layer.
Okay, so yes, the first one. So it's a VGG because we don't want to retrain this one. So from this table here.
So it's not the line.
Yeah, we can also use 0, but actually at that time I was adding layers and removing layers and changing the size of nodes in each layer. So this was sort of hit and trial method. So at that time I left it -6. I don't know why. Yeah, it can be 0. You are right.
Yeah.
It means the same thing.
Yes. So we have 6 layers here. So it's this one. VGG. We will not retrain it one more time. It will save huge time. Because also if you will return it, you will destroy it. You need to use it as it is. Because VGG 16, they have been training it using AlexNet, Muhammad?
Yes.
It has been trained using AlexNet, and AlexNet is millions, like this million of images. So it's a huge. Okay, Muhammad. So the output here, we have 4 outputs. Those 4 outputs for the 4 coordinates of the minimum bounding box. X minimum, X maximum, Y minimum, Y maximum. Yes, Muhammad.
So after that, I compile the model and set the mean square error because I was not classifying it on basis of correct classification or wrong classification. I was just saying where is the error from the actual value that it should predict. So after that, I set the optimizer to Adam.
So just 1 minute, Muhammad. Mean square the error because we try to predict it. We are not classifying. We are predicting.
Yes.
We predict X minimum, X maximum, Y minimum, Y maximum. Yes, Mohammed.
So after that, this is the training part. Okay, so this happens when you don't use the GPU for a time and it disconnects. So you have to disconnect it again probably. Okay, so but we have done it already. So this is the training part. And after that,
we plot.
I have plotting is done in the end. So I have just tested, evaluated it on my test data, and then I have plotted these results here.
Okay.
So this is my accuracy score, and this is my loss.
Okay.
So we can see that model doesn't learn much after, you may
certainly.
say, 30 epochs. It doesn't do anything. So, but this was some sort of confusion because the accuracy keeps on oscillating. I don't know. I can't understand that if I should increase the epochs or it need more data. Probably it needs more data because uh, it is not performing much well on. It has become stagnant both.
Okay. So data augmentation, is it possible to use data augmentation here in Python?
Sorry, I can't understand you.
Data augmentation, data augmentation.
It didn't.
I stay.
No, we didn't use.
Yes.
Data augmentation.
No, I haven't used.
Okay, okay. This is very good. This is very good exercise, in fact.
Yes.
It will be nice if you can have an example. Did you plot an example here for an image?
No. It's generated.
Muhammad.
Yes.
Okay, so this is X test. There's also some images. Y predict it will be coordinates. Did you plot it for one image or something? Okay, but maybe.
Yeah, I have uploaded results. You can see.
Okay. So this is the performance.
Yes.
So the idea here, we have an image and we try to predict the coordinates of the minimum bounding box. So we can just focus on that part. And after that, they will use, text and something for reading, for converting the license plates into a text. So it works. In some cases, it works very fine, and in some other cases,
yeah, it does not work too well. That's why we moved to the other mask RCNN, because also that we haven't worked on, like, for example, that we haven't worked on something like data encoding as auto encoding, and also we haven't done much about data augmentation.
Yeah, I just want to say something about using mask RCNN. I mean, mask RCNN, it's very smart, especially working with like time series, for example. So if you are working with a video, so we have a frames, number of frames per second, for example. So if you want, for example, we can have this application. Maybe some of you can do it because we are still have some weeks to the end of the course. So for example, if you have a video, surveillance, how do you call it? So if you want to track a person in different frames, so you just extract features from some frames and you try to track him in the rest of the video. So in this case, we can use mask RCNN, and it will be very, very good in this. Because the person, we will get all information from the person from some frames, and after that, we will track him in the rest of the frames. So this is how we do it for tracking people.
How about using optical flow? Optical flow.
Optical flow?
It's a simple image processing technique.
Yeah, I mean,
it could be more, I guess, faster. And I guess this type of data, like, it should be processed on real time.
Optical.
So, yeah. So that can be tried.
Yeah. Okay, Mohammed, do you have any? Do you have the code also for RCNN? Or it's?
Yeah. Do I need to share it now?
Do you want to see it, or? Well, this one was very educative. In fact, this example was very good. Okay, I guess.
Because this is the one, the basic one, while the mask RCNN was also taught by Meng Tao during the lab.
So do you have results from mask RCNN?
You could share it if you have to allow, because that's the data set is mounted on that the model is mounted on his drive. It would be better if he could share it.
Okay. So, but anyway, this is very good, and thank you very much for the good work, Mohammed and David.
Thank you very much.
Thank you.
Thank you very much.
Okay. So if you can share this collab with me later on, it would be great. So we can add it to.
Yeah, I can share that.
Okay, thank you very much. Thanks, Mohammed.
Okay, I have a question that, for example, if we want to extend the scope, or like, for example, right now we were just focusing on the license plates. So in the future, within like before the presentation, if you want to extend the scope and change into others, because I was thinking that we are all doing the same sort of license plate recognition, but I have seen that others are doing much more like meaningful or other that have more impact. So can we
Applications?
switch? Yeah.
Yes,
So
no
can
problem.
we
Yeah.
switch or extend it?
Yes, yes, you are free. I mean, the most important is to really make good project. So just select the topic, the task, and the data set. So you are free to just. But I wish at the end if we can build a demo. I wish if we can all together we can build some demos, for example. So if you want to go for face recognition, if you want to go for any task, it's fine. But the most important is to try to build 1 or 2 demos by the end of this course, for example. Those demos will be running here in the lab all time. So it will be nice. So you will have your name here. We will have a demo, and people can just come from outside and test it, for example. Because sometimes we bring kids from schools. It would be nice if we can have some demos so kids can play with it, for example. And so, but you are free to just to select. The most important is to use the techniques which we are learning, and also try to expand and go beyond it.
Okay.
So you are
Thank you
fully
very much.
free, Mohammed. Yeah. So thank you very much, Mohammed and Leo, for your project work. And we can go for the next one. So the next project, it's Nicolo.
Yes,
So-
can you hear me?
Yes, yes.
Okay.
I didn't ask people online. Anyone online has any questions to Mohammed and Leo? No questions from online. You are just unmute your mic and please ask questions or raise your hand, for example. Yes. I don't know how can I change the setting for everyone to share screens.
Okay, Ibrahim, I was the
Yes.
co-host and I changed the settings. Now, if anyone can share, I guess.
You fixed it already.
Yeah.
Okay. Thanks.
I hope so. I hope so. I have fixed it.
Okay. So Nicolo now is sharing his screen. Yes, Nicolo. Here you are.
Unmute. Yes, I forgot the unmute button. Okay. So this is my project. It is about helicity recognition in intergalactic turbulent magnetic fields. This is a project that is developed in collaboration with NTNU in Trondheim, the Department of Physics. And the idea of this project, as I will also explain now, is that in galaxies there are some magnetic fields. Those magnetic fields are turbulent magnetic fields because they move through time, so this generates turbulence. And there exist some theoretical models about those magnetic fields which are currently tested. So it is difficult to say for physicists how strong those magnetic fields are because there are several hypotheses that are currently being tested. And the idea basically is that from a physical point of view, it is quite difficult to simulate turbulence using an analytical approach, because turbulence is something very complex, especially for large systems with many particles or many bodies. And for this reason, there is a simulator that has been developed by Professor Kakeges in Trondheim. This simulator is called ELMAG, and the idea is to simulate this turbulence using random number generation. So there are some complex formulas that I don't fully understand that are able to generate those magnetic fields. So the idea of this project, as I was saying, is to recognize the helicity of those magnetic fields. In the next slides, I will show exactly what I mean by helicity. I think that images make it more clear. The problem is that for strong magnetic fields, the helicity is a property that can be seen, that can be observed in a clearer way. Because in this case, what happens is that if you have a strong magnetic field, you have a shape that is very well defined. While if you have a very weak magnetic field, this shape is not so well defined, it is a bit blurred. And so you have more difficulties in finding the correct value for the helicity. So right now, the actual method to address this problem can be, for example, looking at those graphs that are generated by this tool, or looking at graphs that are obtained by astrophysical observations, and try to understand the value of the helicity, or better, the orientation of the helicity that can be positive, negative, or possibly zero. But the idea is that for large quantities of data, especially when the situation is not very well defined, it is also important to have an automatic and reliable tool for automatic data analysis, which is much faster than a person that tries to say if the helicity is positive, negative, or zero. So currently, my work is based on this article that is on arXiv. The idea of this article is to propose the so-called Q estimator. So an estimator in physics is basically a formula which estimates a certain characteristic of a body or of a system in general. So the Q estimator is a formula that takes 3 points in this plot. Those points represent particles, and tries, and on the basis of those 3 points, tries to detect the helicity on the basis of the reciprocal disposition of those points. This method, those 3 points then can give a result that is positive helicity, negative helicity, or zero helicity. This procedure is repeated for many times, for example, 500 times, 1000 times, and this is basically performing a Monte Carlo simulation. So the idea in this case is that this simulation is performed several times. Several values for the Q estimator are obtained, and in this way, a distribution of probability for the positive helicity, the zero helicity, and the negative helicity are obtained. So in this way, it is possible to say which is the probability that the current shape, the current points represent a positive, negative, or zero helicity using this statistical method. This research, the one proposed in this article, starts by focusing on a toy example, which takes a very simple case in which it is evident that the helicity is positive, for example, and then considers several cases. And it is shown, as I will show in the next slides, that in some cases, there is a significant overlap between the distributions for the values of the Q estimator. And this basically means that if there are significant overlaps, then it is very difficult to say if there is a positive, negative, or zero helicity. So the idea of the machine learning part, okay, this is the distribution I was talking about. So the blue bars are obtained using are obtained for the positive helicity. So the idea is that the Q estimator is calculated many times, and the blue bars represent the values that have been obtained. So the values of the Q estimator that correspond to a positive helicity. This means that, for example, the 3 points that have been taken at a reciprocal disposition, which was, for example, clockwise. I don't remember if clockwise or anti-clockwise or counterclockwise, but one is positive and the other one is negative. As you can see, in this case, there is a significant overlap between the red bars, the yellow bars that are the one corresponding to zero helicity, and the blue bars. And the curves here are just an interpolation of those bars, assuming that the distribution is a Gaussian distribution. In this case, the overlap is 75%, and it is quite difficult in this specific case to say, okay, this is positive, negative, or zero helicity, because if you take a point, for example, here, I don't know if you see my pointer, but if you take a point that is in the center, that or a set of points in the center of this graph, you have the red bars, the yellow bars, and also the blue bars. So for this reason, it is difficult in that case to say the kind of helicity that you have. So the idea is that doing this requires some computations, because for each graph you need to find, for example, 500 points in order to detect the helicity. For more difficult graphs, there are also cases that I haven't reported here, in which those 3 curves are very well defined and very separated. There are small intersections because, of course, since this is a Gaussian curve, it goes in both directions towards infinity. But those intersections correspond to a very low probability, so we don't care about them. So the idea of machine learning is that once the model has been trained, of course, it requires some time to be trained, but after it has been trained, it is able, we can apply the model given an image that is a plot obtained by the data generated by the simulator. And it is possible to say, okay, this is positive helicity or negative helicity or zero helicity. As I was saying before, detecting the helicity is more difficult for low magnetic fields because of the fact that there is more like blurring. So it is easier to say, for example, that a positive helicity is negative and vice versa. So the from a theoretical point of view, the minimum value for the magnetic field is expected to be in the order of 10 to the minus 15 Tesla. I have focused on 10 to the minus 14 Tesla at the beginning, which is one of the other possibilities. This magnetic field can range between 10 to the minus 15 Tesla to 10 to the minus 12 Tesla, if I'm not wrong. So the idea, as I was saying, is that given the magnetic field and other parameters that I didn't change in the simulator, this simulator that is called LMAG 3.0.3, that is not available yet. There is version 3.0.2 that is already available. This one is not available yet because it is quite recent. I think it has been finished this August or anyway in 2020. And the idea is that for each set of parameters that I give as an input to LMAG, the LMAG generates a file in which you have 3 columns that are the X and Y positions and the energy of the particle that can be found in that particular position. I'm not using the energy right now. I mean, in the plot, I also plot the points with different colors on the basis of the energy. But the differences in the energy are so low for the majority of the points. I mean, many points have the same energy or similar energy, that I don't think they're very relevant for the machine learning part, because you see that the graph is almost entirely blue, and there are only a few points, very tiny points, that can be maybe yellow or something like that. But the energy should not be very important for the detection of the shape. And so the idea is that those data are generated, and given the same parameters, it is possible to generate different plots, because of the fact that the simulation of the turbulence is performed using random numbers, and for this reason, every time I obtain something different. And for this reason, I have been able to generate 15,000 different graphs, starting from 3 different parameters for the helicity, so a positive, negative, and zero helicity. In this way, since the helicity is an input for the generation of the output, my data are already labeled. So there is a label that is for the image, for the entire image. It is not a bounding box, but I can generate all the labels I want. And I can probably show, okay, this is the data set. So as I was saying, right now there are 15,000 plots, which I divided into trade validation and test set, 3 possible classes, so positive helicity, negative helicity, and zero helicity. Zero helicity is more challenging, because sometimes it is very similar to positive or negative helicity. As a test, I have tried to generate some data with zero helicity. I sent one of the samples to this professor that studies those topics, asking him what kind of helicity it was. It was a zero helicity, as I will show you, and he thought it was a positive helicity. So it is not very easy to detect zero helicity, not always, unless there are some errors in my code, which is also possible. An example of helicity is this. So in this case, you can see that this is a positive. I don't know if you can see, because it is quite small, but this is a positive helicity, because in case of a positive helicity, you have a shape like this. Can you see my pointer?
Yes, we can see.
Okay, you have a shape like this, possibly rotated. So you have some particles here, and then something like this. Well, for a negative helicity, you have something like this. And of course, you can also rotate it. And so for a negative helicity, you can also have something like this, and so on, all the possible rotations. While this is a clear case of zero helicity, in which it is flat, basically, outliers apart. And this is also a case of zero helicity, but as you can see, this can be easily misunderstood by another kind of helicity. I think, yes, it is can be misunderstood as positive helicity, while it is not positive helicity. Another important thing is that before generating those plots, I have done some filtering, because you can see that there are some outliers here that are separated from the main plot. There were much more outliers. So my filter says that if you the farther away you go from the origin, that is this point 0, 0, that is always the origin for all the plots, the higher is the probability that you discard the points. So I've seen that in this way I can remove some points that are not important for the helicity detection. So yes, this was the test, and shouldn't have anticipated it, as this, otherwise it is not as funny. Anyway, so this is my proposal. My proposal is to work with the generated plots. I also have the tables with the data, but I think it is more challenging to work with them, because I don't have always the same points. Also, the points are random points. So I cannot like flip the table and say, okay, I have, for example, 5,000 points for each table, and I use them as columns, and then I have a very big table with the rows that are samples and the columns that are, for example, the rows that were inside the initial table for one output of the simulator. So what I've thought about is using images, even because it is important in this case, not only the data taken singularly, but also the relation between the points. And so this is very appropriate for an image indeed. There are many convolutional neural networks to work with images. I have tried some models to see the differences in the results. The results have been quite similar. The only difference is that some models are a bit faster than others. Others instead take hours and hours and hours, even with the GPU. And my idea later, once I will have better results, is to use CAM, GradCAM, and GradCAM++, and possibly also Smooth GradCAM++, that are also all variants of CAM, and I will present CAMs now, in order to locate the points in the image that contribute the most to the decision of the network. For example, if there is a positive helicity, as in this case, then a CAM will highlight, it is a sort of heat map, and it will focus on this area and this area, because those ones are the one that allow to say this is positive helicity. We don't care about this part. I mean, the network shouldn't care about the flat part because it is the same in all the graphs, but it should care about this area and this area. And for the negative helicity, probably in this area and this area. So those are examples of CAMs. So as you can see, they're not related to this specific project, but CAMs can be applied in many fields, for example, medicine. So in this case, you see that, for example, in this case, probably the idea was to locate those points, those white points, and the CAM focuses on those points, because the CAM is something that can be applied after the network has been trained on the basis of the activation maps and the feature maps and gradients, possibly gradients in the case of GradCAM, Smooth GradCAM, and Smooth GradCAM++. Another application is phenology. So in the case of phenology, you can see that this heat map or CAM is activated when you have the plant. And also in the case of astrophysics. So in this case, this should be an astrophysical object. That could be anything, actually. I am not sure. And this is the original image. And this is the CAM, or I don't know if this is CAM, GradCAM, GradCAM++, or Smooth GradCAM++. The difference is not a huge difference in terms of visualization. So my current approach is to perform analysis on a magnetic field that is in the order of 10 to the minus 14 Tesla with turbulence. And I tried both with two classes, so positive and negative helicity, which should be easier, and three classes also with zero helicity. The problem with zero helicity is that you can have the same case as before, with some cases in which it could be easily misunderstood by positive or negative helicity. I don't use a very high amount of points for this because for each graph, I mean, because otherwise it takes a lot of time to generate the outputs. So at the beginning, I tried to use a low amount of points. Probably if I used more points, I would also have had better inputs and so also better outputs. So I would probably try with more points as well. So this one is my result. So my confusion matrix for the two classes cases. I used network that is ResNet 18. The optimizer is Adagrad with a learning rate of 0.01 and a learning rate decay of 0.0004 with 38 epochs. I have reached more or less the same results for the validation in 21 epochs, but I've decided to keep training as an experiment. It overfits for the train accuracy because the train accuracy is very high and the validation accuracy is much lower than the train accuracy. But anyway, I haven't been able to obtain better results for the validation accuracy in previous epochs. And the test accuracy is 84% in this case. So you can see that it is quite good in detecting whether the edicity is positive or negative. And I also tried with GoogleNet. As you can see, the results are more or less the same. So the train accuracy is also in the order of 99.9%. Validation accuracy in this case is 85%, well, before it was 84%. And the test accuracy is always 84%. And the number of epochs is exactly the same with the same optimizer. And this is with GoogleNet. For the three classes case, the results are worse than before because my test accuracy is only 57%. As you can see, the problems are always with the zero helicity. I don't know if this is caused by the fact that maybe the simulation is not very precise. Maybe I would need more points. I'm investigating several possibilities. But as you can see, there is a low confusion for negative between negative and positive, as you can see here. And when you have the zero, then you have more confusion. The reason why you see 0 negative, 1 0 and 2 positive is not to create confusion. It is just because I wanted to order the three classes, because right now I use cross entropy as loss function, which doesn't care about the order of the classes. But one of the possibilities I was thinking about was to give a different loss depending on the distance. I mean, maybe I can assign a greater loss if I say that something is positive while it is negative, or vice versa, and a smaller loss if I say that something is negative while it is 0, or positive and 0, because actually negative in the reality is closer to 0 than to positive. So this is the reason why I've sorted the classes in this way. Otherwise, they were sorted alphabetically, and so I wouldn't have been able to do so. So those are some ideas. I don't know if they make sense. So one is to generate better data. I think this can make sense, even if it takes more time and more memory. Another idea is performing the classification on 2 classes and testing on 3 classes. I don't know how to do this. I tried to do this, but with the model trained for the 2 classes, but I should readapt it because there are some problems with the dimensions of the tensors. Try other network models. This is something that I started to do with GoogleNet, for example, and I've also tried DenseNet, but I also always obtain more or less the same results. Try other optimizers. I've tried Adam, Adagrad, and AdaDelta, or also Adagrad with other parameters. A stronger magnetic field can definitely help because, according to the theoretical, the theory behind this, a stronger magnetic field means a more definite shape. So maybe I will try with 10 to the minus 13 and 10 to the minus 12 as well. Improve the data filtering, the thing that I do to remove the outliers. Maybe that can create some problems. Or maybe I should use the same scale for all the graphs and try to do this automatically, because I don't want to set the scale at the beginning for each graph, because there are 15,000 and I don't want to spend a lot of time deciding the scale by hand. Or another possibility would be to adopt another approach which does not rely on computer vision. This is like the last possibility because I should change everything, and I don't see many advantages in this because it is important to consider the relation between the points, and the helicity is a property that can be observed in an image. So I think that for this reason, it makes sense to use computer vision. And finally, those are the results I have obtained if the learning rate decay is set to 0.04. So as you can see, the training accuracy and the validation accuracy look quite promising. But the problem is that the test accuracy is very low. It is 47%, which is actually very bad for two classes because if I try to guess, I obtain better results. So it is not very, I mean, there is no purpose in training a network to have something worse than my guess. And the same for the three classes cases. So 0.04 as the decay is definitely not a good idea. And that should be all.
So I want to ask you a question, and just because before forgetting,
Yes.
when you split the data, do you get this equally represented? I mean, all classes are equally represented.
Yes. Yes. At the beginning, when they generate the data, they are generated randomly. So more or less, there is the same amount for positive, negative, and zero.
I know, but
and then when I split this, the same happens.
When you split, do you use Stratify?
Sorry, can you repeat?
When you split into training, testing, and validation, do you use this option which is called the Stratify?
No, I'm using Torch for this.
I'm just worried because for this A and B here in this slide, maybe some classes are not represented here.
No. This is not. I've checked this. This is not a problem. The problem in this case is just that the decay is very high, I think. But
Okay.
all the classes are represented actually. They're not exactly the same numbers because they're generated randomly, but there is a very small difference.
Okay, very good.
I can show it to you because I've saved the models that worked, and I can show you the way which I've obtained those graphs.
It's just very important when you split your data into training, testing, and validation. You need to use this Stratify equal y. When we use Stratify equal y, it means we will get all classes represented in the training, testing, and validation.
Okay, I haven't used explicitly this option, but they're equally represented because of the fact that they've been generated randomly.
Yes, so, I know. I mean, we have 50, maybe 5,000. It's in total 15,000, which means 5,000 plus 0, positive and negative. So it's equally. But I mean, when we shuffle and split, we need to be sure that each cluster is equally represented in the training. So we can do it if we will use this function from sklearn, if we will use a Stratify equal y. In this case, we will be sure that all classes are equally represented. Okay. So I have notes, a point for you, Nicolo. You are working with image, and you suggested that maybe you can work with data points instead of working with images. In this case, please try to use some higher order features or interactive between features, because we have X and Y coordinates, and if you can see it in my board here, I mean, this is positive, we will have this shape, this is negative, and this is
oh wait, I'm trying to see your board.
Yes. I don't know if I will try to zoom more, but I don't know if you can see it.
No, it is at the
yes,
with my screen.
Yes, do you see? So we have here, this is positive.
Please wait just a moment.
Can you see my
screen? I'm trying to enlarge your
because we are not sharing. You are sharing. I need to share. Can you see my screen? Can you see my?
Oh yes. Now I can see. I had to change with speaker view. Yes.
Yes. Do you see? This one is a positive. Let's see. This is negative, and this is 0. And
yes.
And we have two pictures. We have X and Y. So we need to try higher order features. Maybe if we will use x1 square, x2 square, it will be easy to classify.
Yes.
We need to use interactive interaction between features. Maybe x1 times x2, it will help us. So we need to spend the time because it looks like, I can see it here. So we have one positive class, we have zero class. So we need to try, instead of working with xy directly, you need to try some interactive features and higher order features. So try to generate x1 square, x2 square, maybe x1 times x2. So try to, do you know those select k-best? Do you know the methods which we represented one time? There are many methods, but here in the classroom we used to only select k-best. So try to generate some features from, because we have only, I mean, Niccolo is working only with x and y. He didn't use energy. He has x, y, and the energy. He said energy, there is no difference in the energy each particle. So we will focus on x and y, and it will be easy to put it in x, y coordinate, in two-dimensional coordinate system. But instead of working with x and y, we need to try other features. So try x1 square, x2 square, x1 times x2. Try to use higher order features, and we will see maybe we can simplify it from the beginning, and it will be much easier.
It's a continuous like this.
Yes, it's a points. It's not continuous. It's a discrete. But we have points, and those points should look like this shape when it's positive. It should look like this shape when it's negative, and it should look like linear. For example, when
The point should be in a specific trend to identify it.
yes, each cluster has a shape.
So how about using LSTM?
LSTM. Oh, for the whole set.
So if you have one point and you keep the one point in the memory and analyzing the second point.
This is also good idea, Niccolo. So Hamad, he mentioned that you have a set of points and they are generated. They have like a trend or something. So maybe if you can try LSTM long short-term memory. So in this case, maybe it will be also a good idea. So first, you need to try before generating your image. You are working with images, but before generating the image, I just propose that you need to try first different combinations of x and y, different features combinations. Maybe it will make it more simple. Because x, y, maybe it's tough to classify it now.
You can apply simple LSTM on the data point instead of generating the images.
Yes, that's correct. And also, I propose also to try first to try different combinations of x and y. Maybe it will make it simple, right? So there are many methods for doing this. So instead of working with x and y coordinates, we will, because we have big confusion between zero and the non-zero, right? It's okay, we have very good accuracy when it's positive and the negative, but we have confusion between zero and the positive and the zero and negative. This is the problem. So maybe if we can use some feature construction techniques and selecting the best combination of features, maybe it will be more simple. So this is one direction. The other direction also is to work with the raw data and using, for example, some recurrent neural network. Maybe it will, and in this case, you don't need to convert it into an image. So you have those two options. And also, you have sometimes a problem of overfitting. You said that it's after 30. So you need to use early stopping. You need to include early stopping. So if your model starts to overfit, you stop training. So you need to use this layer in middle of, this is very, very important.
Yes. What I observed, I haven't introduced early stopping already yet, sorry. But what I observed is that even if it looks like it starts to overfit, if I keep it running, sometimes, well, often it improves. The validation accuracy improves, and also the loss improves after some time. This is why I haven't implemented it yet, because even if it doesn't look promising, I have let it run, for example, all the night, and sometimes it remained flat for like 50 iterations, and then it started to show better results. And as for the feature selection you're suggesting, I think this is a very good idea. My only concern is that would like to understand before if the problem is maybe related to the quality of the input data, because if as in the example that I shown you before, if there are some data that are very similar to a positive helicity or negative helicity, maybe the reason is that I don't have enough points. And so maybe if I generate more points with the simulator at the beginning, I will still have those points, but those points will be maybe inside the line, while generating more points, I will have also more clear shape. So before doing that, I would do this because you saw that the shapes were very similar. So I think that even if I try this method of feature selection, changing the X and the Y, then I could run into the same problem because of this, because if the initial data are very similar, also the output data can be very similar in this case. I don't know if this makes sense.
No, but each class in fact has a shape, right? So each class has, when you display those images, I feel that positive will look like this, negative will look like this. So there are some differences, but maybe, because the number of points, it's only 500 points for each class, maybe it's not enough really. If you can generate more, the shape will be more clear. But, but as you mentioned, maybe you can try to generate more points. And also, we need to try feature selection, for example, right? And as Hamad mentioned, also maybe we can try LSTM. So maybe with LSTM it should be, because when it's linear like this, it should be, it's like regression problem effect. So it could be possible to decide if it is which it is.
Yeah.
So, by the way, the professor in Trondheim, did he see, the initial results which you got?
I've shown him I've sent him all the images, but I don't think he have looked at all the 15,000 images. So the problem is that, as I was saying before, for the image that yes?
No, it's the accuracy of the models. Did he look into it? And because maybe he is a domain expert, maybe he is very good in what he is doing, for example, and he can just say, okay, 50% is very good. Maybe 70%, maybe the problem is really different. And then when we build a model which can assist the people and they provide accuracy of 60%, it's big achievement. I don't know. So the domain expert, in fact, he should look into our results and decide if this is good enough or not.
I've asked him about the accuracy for the lowest magnetic field. The for 3 classes was also around 60%, and he told me that those results were in accordance with the theoretical results, basically. So they should be maybe not so bad, but I would expect, at least for higher magnetic fields, to have better results. But I still have to ask, because maybe it is not possible to do better if from a theoretical point of view, it is not possible to go to have more than 60%, for example. In that case,
I agree with you.
There is nothing we can do, but
in this case, in fact, you need to provide a table for each spectrum. How do you call it? Spectrum, or to generate it for how do you call it?
The distributions of the Q estimator, yes. But I still have to ask about this, because I ran those tests, the last ones, in the last days, so I didn't have enough time to ask him to check those results as well.
Okay, so thank you very much.
Thank you.
This is very good. In fact, this is cutting edge research in this area, and my feeling that if this is the first application of machine learning in this area, it will be highly cited, and it will be very important to make some contribution in this area. Because because you did some literature review already, Nicolo, and you feel that you said that maybe it's no more applications. No one did that before in this specific area. So if it is the first time to use machine learning in this area, it would be very good. Any questions to Nicolo? Any questions?
No.
Mhm. So by the way, Nicolo, is it possible to build a model to classify zero and non-zero? And it might help to just differentiate between zero class and the non-zero class?
Yes, this can be a good idea as well. Of course, the data would not be balanced in that case because they're balanced for, you know, 0, positive and negative. So I would have double of the data for positive and negative in that case. But I think
what about multi-class classification?
Can you repeat, please?
Multi-class classification is also a good idea because in this case we will build a model to classify zero against the rest, positive against the rest, and negative against the rest. This one versus the rest. Do you remember it?
Yeah.
OVR. It's called one versus the rest. So,
Yes.
so in this case we will have 3 models, one for each class.
Yeah, I agree with this. This is also a good idea. My strategy now would be to ask this professor about the reason why some data are maybe unexpected, if this depends on the number of points or other things. If he tells me that that even with more points I wouldn't obtain better results, and that the results I obtain are, for example, the best possible results from a theoretical point of view. I don't think it is like that, but maybe I want to be optimistic. Well, in that case, probably there is nothing more I can do to improve the results if they're the best possible results from a theoretical point of view. Otherwise, if it tells me that maybe I should generate more points, I will also try with more points. I will also try to transform the data to see if there will be any difference, and also I will try to detect zero or non-zero class and so on, as you suggested.
Yeah.
I think I see that there is a question on the chat. What
Okay.
are ResNet 18 and GoogleNet? So ResNet 8, I'm not an expert in ResNet 18 and GoogleNet, but the idea is that ResNet 18 is a residual network. And the idea of a residual network is that you have all the layers, like in a sequence, but you also have the possibility to jump from one point to another point that is not directly connected in a sequential way. Ibrahim probably knows this better than me, and maybe I'm saying very bad things, I hope not. But the idea anyway is that you can, that in this way, it has been demonstrated that with ResNet, you can obtain better results, for example, in terms of localization of objects. For my master thesis, for example, I'm working with ResNet 50, and the idea in this for the detection of, for example, subjects inside artworks, and it has shown good results because it is able, for example, to detect a specific character. I'm working with Christian Saints because my thesis is about iconography. Well, it is about the iconographical meaning of works, but it takes too long to explain. So in that case, it has shown good results in detecting objects with different maybe orientations and different positions and so on. So it is good at localizing things. And I thought this could have been useful for this case as well, even if maybe a bit too powerful, a bit too complex for this case, which is simpler. Because as you have probably seen in the examples, the zero is not necessarily at the center of the plot. So you can have those plots in several locations. You can have different orientations. For example, the positive helicity graph that Ibrahim has drawn can also be rotated, of course, and it is always, it keeps the same helicity. And so I thought that this kind of network could have been useful for this. And I think that it is quite good after all, because in the case with two classes, it has achieved a good accuracy after all. And GoogleNet is something similar. I think it is always a residual network. I'm not an expert about GoogleNet because I have just tried several models, but I haven't looked into the structure in a detailed way. But I think it is always a residual network. I think it is maybe simpler than the residual, that ResNet 18. But yes, this is what I know.
So this is very important, Nicolo, maybe for Mohammed and Leo, because they are using this localization of I mean license plates, for example. Maybe they can try ResNet 18 or ResNet 15. Because
Yeah, I think this
this
simplicity.
is good for I mean not aligned, I mean perfectly aligned images, so it will be really very good. So Mohammed and Leo, so please try to test this ResNet 18, for example.
Yeah, it takes some time to train, because
it's a pre-trained, correct?
yes, I have tried with the pre-trained version for both of them. I also tried to train them from scratch. I see that with 16 gigabytes of GPU, so two GPUs with 8 gigabytes each, it takes about no, well, I've used only one GPU, so 8 gigabytes. It takes 4, 5, or 6 minutes, up to 10 minutes, let's say from 4 to 10 minutes for a batch with for an epoch actually. So yeah, it can take some time for like 100 epochs or something. So some hours usually.
Yeah. Okay, thank you very much, Nicolo. Any questions from the classroom? Any questions? Okay. So thank you very much, Nicolo, for your nice presentation. It was very informative today, in fact, because we have been exchanging emails, but today it's very much easy to understand. So now we will take 10 minutes break. You can just grab your coffee, and we will meet again at 10 past 10. Yes. So thank you very much for joining. We will meet again after 10 minutes.